Hello students, welcome to mathematics class. Today we will discuss about partial derivatives. Partial derivatives. And before discussing partial derivatives, let us have a look at ordinary derivative. You all know to find ordinary derivative of a function. For example, if you are given a function of the form y is equal to f of x. Suppose y is equal to f of x is a function. That is, y is a function of a single variable x. Y depends on x only. So in this function, we call y as a dependent variable and x as an independent variable. Here y is a function of a single variable x only. Then for this function y is equal to f of x, how will you find its derivative? We know that the first derivative is denoted by, we denote the first derivative by y dash, or this y dash is equal to, we can also write it as f dash of x. And we know the definition of derivative in terms of limit of a function. We know that f dash of x is equal to, what is that? It is limit delta x tends to 0, f of x plus delta x minus f of x divided by delta x. That is the definition. F dash of x is equal to limit delta x tends to 0, f of x plus delta x minus f of x by delta x. Using this definition, we can evaluate if this limit exists, this derivative exists. That is the definition, right? That is, if we define the first derivative f dash of x as the limit of f of x plus delta x minus f of x by delta x as delta x tends to 0. If this limit exists, we say that this function y is equal to f of x is differentiable and its derivative exists. That means y dash exists. Okay. So here this function y is a function of a single variable x only. Now in this section we are considering functions of more than one variable. That is, we are considering functions of z is equal to f of x y. So here z is a function of two variables x and y. Z depends on two variables x and y. So here z is the dependent variable and x and y are independent variable, right? So here there are two independent variables and one dependent variable. So in this section we are mainly concentrating on these type of functions and we find derivatives. So here, since there are two independent variables, we can find derivative of this function z with respect to x and with respect to y. Okay, because z is a function of two variables x and y, so we can find derivative of z with respect to x and also derivative of z with respect to y. Now, so here I have defined what is an independent variable and what is a dependent variable, and the set of ordered pairs xy, that is called the domain of this function, and also the set of corresponding values of z, that is called range. And what about the graph of function of the form z equal to f of xy? We know that since there are three variables x, y and z, that graph will represent a surface in the three space. If we are considering the function y is equal to f of x, what will be its graph? Its graph will be a curve in the xy plane. That means in the two space. A graph of any function of this form y is equal to f of x will be a curve in the two space. But here, since we are considering three variables, here z is a variable, x and y are two variables. So here, in order to draw the graph of this function, we need xyz plane. So what we get? We will get a surface in the three space. Now, for a function z equal to f of xy, the curves defined by the equation f of xy is equal to c for suitable c. These type of curves are called level curves of f. Level curves of f. That is, level curves of this curve z equal to f of xy is a curve of the form f of xy is equal to c, where we can put any values for c. So corresponding to different values of c, we get different level curves. So here z equal to f of xy, that is, z is a function of two variables x and y. Now we are considering functions of three or more variables. Now the functions of three or more variables are defined analogously to functions of two variables. For example, suppose w is a function. Here w is equal to f of x, y, z. That is, w is a function of three variables x, y and z. Here, what are the independent variables? X, y and z are the independent variables, whereas w is a dependent variable. So here w is a function of three variables. In the same way, we can define a function of four variables. Suppose there is one more variable t, one more independent variable t, then we can, if we define w is equal to f of x, y, z, comma t, then what we get? We get a function of four variable. So here the x, y, z, t are independent variable, whereas w is the dependent variable. So in this way we can define functions of several variables, right? Now we define what is a level surface. So already we defined what is a level curve. Now we are going to define what is a level surface. So a level surface, we know that surface to draw a surface, we need a three space, that is a xyz plane. So the surfaces defined by f of xyz is equal to c for suitable values of c. These type of surfaces are called level surfaces. So a level surface means a surface of the form f of xyz is equal to c. Now we will do examples. First example, describe the level surfaces of the function f of xyz is equal to x square plus y square divided by z. Describe the level surfaces of the function f of xyz is equal to x square plus y square divided by z. So, for c not equal to 0, the level surfaces are given by, what is the formula? The form of a level surface is f of xyz is equal to c. So, here f of xyz is equal to x square plus y square divided by z. So, this function is equal to c. This is the form of level surface. So, we get x square plus y square is equal to zz. So, this is when c not equal to 0. So, the equation of level surfaces here is given by x square plus y square is equal to cz. We can choose any non-zero values for c. Now, what happens if c is equal to 0? If c is equal to 0, the right hand side becomes 0. So, we get x square plus y square is equal to 0. Now, x square plus y square is equal to 0 means that x equal to 0 and y is equal to 0. In that case, we will get just the z plane only. We will not get any surface or something like that. So, here the level surfaces are given by the equation x square plus y square is equal to zz, where c not equal to 0. Next, we are going to define partial derivatives of a function of two or more variables. So, I have already told you that for the function y is equal to f of x, its derivatives, first order derivative, that is dy by dx, is given by this formula, that is limit delta x tends to 0, f of x plus delta x minus f of x divided by delta x, provided this limit exists. Now, here in order to find partial derivative, we need a function of at least two variables. So, here we consider a function z. Z is a function of x and y. So, z is a function of two variables, so that we can find derivative of z with respect to x and also derivative of z with respect to y. So, such a type of derivatives are called partial derivatives, and we define the partial derivative of z with respect to x. Partial derivative of z with respect to x, as we use this notation. This is dou z by dou x. And when you find partial derivative of z with respect to x, we consider the variable y as a constant. We consider the second variable y as a constant. That is, we differentiate this function z with respect to x only. We are treating y as a constant. So, it is given by this formula. We know the dy by dx is equal to limit delta x tends to 0, f of x plus delta x minus f of x by delta x. So, in the same manner, partial derivative of z with respect to x, that is dou z by dou x is equal to, here also since we are differentiating with respect to x, we have this thing, limit delta x tends to 0, f is a function of two variables x and y. So, here f of x plus delta x. So, here also f of x plus delta x comma y is right as it is. There is no change in y, minus the function. Here the function is f of x. So, instead of f of x, here f of xy. So f of x plus delta x y minus f of xy divided by delta x. So whenever this limit exists, we say that the partial derivative of z with respect to x exists. That is dou z by dou x exists. Okay. Similarly, we find partial derivative of z with respect to y as we denote the partial derivative of z with respect to y as dou z by dou y, and it is defined as in the same manner. Limit, since we are differentiating with respect to y, we are considering x as a constant. So limit delta y tends to 0, f of, there is no change in x. So x comma y is changed to y plus delta y minus f of xy divided by delta y. So if this limit exists, we say that partial derivative of z with respect to y exists. That is dou z by dou y exists. Also, we know that derivative of a function represents the rate of change. For example, this ordinary derivative dy by dx represents the rate of change of y with respect to x. Similarly, the partial derivatives also, that is dou z by dou x represents rate of change of z with respect to x, and similarly dou z by dou y represents the rate of change of z with respect to y. Now, to compute dou z by dou x, we use the laws of ordinary differentiation. The only thing is that here y is considered as a constant. And similarly, to compute dou z by dou y, we use all the laws of differentiation, but here x is considered as a constant. That is the only difference. Now let us do some problems. So first question, if z is equal to 4x cube y square minus 4x square plus y raised to 6 plus 1, find dou z by dou x and dou z by dou y. So we have to find first order partial derivatives x with respect to x and y. So what is dou z by dou x? We are given z. Z is a function of x and y. We have to find partial derivative of z with respect to x. So here, since we are differentiating with respect to x, we consider y as a constant. So in this first term, this y square is considered as a constant. Then we need to only differentiate the term containing x, that is x cube. Here 4 is a constant, y square is also a constant. Then we just find derivative of x cube. What is derivative of x cube? It is 3x square. So derivative of the first term, partial derivative of the first term with respect to x is 4y square, that is a constant, into derivative of this, that is 3x square. Now the second term is minus 4x square. So here there is a term of x square. This 4 is a constant. So what is the derivative of this x square? 2x. So 4 into 2x, that is 8x. So we have negative 8x. Then what is the derivative of the third term? Third term contains y only. It's a function of y. Y raised to 6 here. So since y is a constant, this term is also a constant. So derivative of third term is 0. And also fourth term is 1, that's a constant. So derivative of fourth term also equal to 0. So what is the partial derivative of z with respect to x? That is dou z by dou x is equal to 4, multiplying we get 12x square y square minus 8x. So this is our dou z by dou x. So here we treat y as a constant. Okay. Now next to find the partial derivative of z with respect to y, that is dou z by dou y, and it is equal to, let us find the derivative of partial derivatives of each term one by one. So the first term 4x cube into y square. So since we are differentiating with respect to y only, x is treated as a constant. So this 4x square is a constant term into derivative of y square, that is 2y. Okay, plus the second term contains no terms of y. It's a term of x only, and x is a constant here. So derivative of second term will be 0, and the third term y raised to 6. So derivative of y raised to 6 with respect to y, that is 6 y raised to 5, and the fourth term is 1 here, and its derivative is 0. So we get the partial derivative of z with respect to y as 8, multiplying we get 8x cube y plus 6y square. Now we have symbols to represent partial derivatives. We know that in the case of ordinary differentiation, for the function y is equal to f of x, its first derivative is denoted by y prime or y dash, or we can denote also like f dash of x. Y prime is equal to f dash of x. Similarly, we give a notation for the second derivative of this function as y double dash or y double prime, and it is equal to f double dash of x. So in this way we denote the derivatives of the function y is equal to f of x. So in the same manner we have notations for partial derivatives also. So if our function is z is equal to f of xy, then the partial derivative of z with respect to x, that is dou z by dou x, that is the same as dou f by dou x, because z is the function f. So dou z by dou x equal to dou f by dou x, and we denote this partial derivative by zx. Here x is written as a suffix, or fx. So zx or fx means it is nothing but dou z by dou x. And similarly, partial derivative of z with respect to y, that is dou z by dou y, or it is dou f by dou y, and it is equal to zy, z suffix y, or it is f suffix y. So this is our notation, fx and fy, or zx and zy. So these are the notations for first order partial derivatives. Next we are going to consider higher order partial derivatives and mixed derivatives. So here this y dash is for this function y is equal to f of x. First derivative is y dash and second derivative is y double dash. Third derivative is y triple dash, and so on. And similarly we can find higher order derivatives and also mixed order derivatives for functions of the form z equal to f of x. So the second order partial derivatives are dou square z by dou x square. What is dou square z by dou x square? We know that for this function y is equal to f of x. What is d square y by dx square? It is equal to d by dx of dy by dx, right? D by dx of dy by dx. So in the same way, dou square z by dou x square, that is the second order partial derivative of z with respect to x. It is equal to dou by dou x of dou z by dou x. Similarly, dou square y by dou y square, that is second order partial derivative of z with respect to y, that is equal to dou by dou y of dou square z by dou by dou y of dou z by dou y. Similarly, we can have third order partial derivatives. Dou cube z by dou x cube is equal to the derivative of the second order derivative, that is dou by dou x of dou square z by dou x square, and dou cube z by dou y cube is equal to dou by dou y of dou square z by dou y square. Now let us consider mixed second order partial derivatives. So mixed second order partial derivatives means here also we are finding second order partial derivative, but we are differentiating the function with respect to x and y. That is, we are considering derivatives of this form, partial derivatives of this form, dou square z by dou x dou y, and dou square z by dou y dou x. Now let us consider the first one, dou square z by dou x dou y, and it is equal to, so here first we partially differentiate with respect to y, then we partially differentiate with respect to x. So it is dou by dou x of dou z by dou y, and this thing dou square z by dou y dou x is equal to, here first we partially differentiate with respect to x, then we partially differentiate with respect to y. So it is dou by dou y of dou z by dou x. Now there are symbols for these second order and higher order derivatives. So let us see. So for this function z equal to f of xy, this second order partial derivative dou square z by dou x square is denoted by fxx, since we are differentiating with respect to x twice. So fxx, and similarly dou square z by dou y square is denoted by fyy. Okay, so dou cube z by dou x cube is equal to fxxx. Similarly, dou cube z by dou y cube is equal to fyy. That is, here we partially differentiate with respect to y 3 times. That is why this notation. Now, what about the mixed second order partial derivatives? So we consider this thing. dou square z by dou y dou x, and it is here first we differentiate with respect to x partially, then we differentiate with respect to y partially. So it is dou by dou y of dou z by dou x. So what is dou z by dou x? It is fx. Fx. Dou z by dou x is equal to fx. Then so we differentiate this fx with respect to y partially. So this fx y, or it is denoted by fxy. So fxy means dou square z by dou y dou x. And similarly this derivative dou square z by dou x dou y is equal to, here first we differentiate the function z with respect to y partially, then we differentiate with respect to x partially. So dou by dou x of dou z by dou y. So this dou z by dou y is fy. See, we differentiate fy with respect to x partially. So we have the notation fy x, that is fyx. So dou square z by dou x dou y is fy. It is denoted by fyx. Dou square z by dou y dou x is denoted by fxy. Now, if the function f has continuous second order partial derivatives, then this fxy is equal to fyx. That is, if the second order partial derivatives are continuous, then these two will be equal. Now we consider partial derivatives of functions of 3 or more variables. So here a function is written as w is equal to f of w is a function of x, y and z. So here w is a function of 3 variables x, y and z. Okay, so there are 3 independent variables. So we can find partial derivatives of w with respect to x, y and z. And the partial derivatives are denoted by dou w by dou x, dou w by dou y, dou w by dou z. And dou w by dou x can also be written as fx, f suffix x. And similarly, dou w by dou y as fy, dou w by dou z as fz. Now let us do one example. If f of x y t is equal to e raised to negative 3 pi t cos 4x sin 6y, then find partial derivatives of f with respect to x, y and t. So here f is a function of 3 variables x, y and t. We have to find partial derivatives of f with respect to x, y and t. So that is, we have to find fx, fy and ft, and fx is equal to, we are differentiating f with respect to x only. Here y and t are considered as a constants. So the first term is a constant here. What is the term containing x? Cos 4x. What is the derivative of cos 4x? It is negative 4 sin 4x. So negative 4 sin 4x into e raised to negative 3 pi t into sin 6y. That is negative 4 e raised to negative 3 pi t sin 4x into sin 6y. This is the partial derivative of f with respect to x, that is fx. Similarly, fy means partial derivative of f with respect to y. So here what is the term containing y? Sin 6y. What is its derivative? 6 cos 6y. And these two terms are constants. So this constant into 6 cos 6y. So we get 6 e raised to negative 3 pi t cos 4x into cos 6y. Similarly, ft, partial derivative of f with respect to t, is the term containing t is e raised to negative 3 pi t. So its derivative is negative 3 pi into e raised to negative 3 pi t. So negative 3 pi into e raised to negative 3 pi t into these two are constants, cos 4x into sin 6y. So in this way we find partial derivatives. One more problem is given here. Find first and second order partial derivatives of z equal to x square minus 4y square plus 4y raised to 5. So here z is a function of 2 variables x and y. Z is equal to f of x y, a function of 2 variables. We have to find first and second order partial derivatives. That is, we have to find fx, fy, x square, fy square, fxy and fyx. So first fx. Fx equal to dou z by dou x, and it is equal to we differentiate partially with respect to x. So, what is the derivative of first term? 2x. And derivative of second term? In second term is negative x y square. Here y square is considered as a constant. So, derivative of x is 1. So, derivative of second term becomes negative y square. Now, third term is in terms of y. So, its partial derivative is 0. So, this is fx. 2x minus y square. And similarly, fy is equal to, we differentiate z with respect to y partially. So, we get here the first term contains no terms of y. In the first term, there is no y here. So, partial derivative of first term is 0 with respect to y. That is 0. And what about the partial derivative of second term? Here, x is considered as a constant. So, derivative of y square is 2y. So, negative 2xy plus derivative of this term is 20y raised to 4. So, we have dou z by dou y is equal to negative 2xy plus 20y raised to 4. Now, let us find the second order partial derivatives. So, fxx means dou square z by dou x square, and it is given by dou x of dou z by dou x. And what is our dou z by dou x? It is, we got it as 2x minus y square. So, dou x of 2x minus y square. So, differentiating partially with respect to x, we get, what is the derivative first step? 2 into derivative of x, that is 1. So, 2 minus dou x of y square, that is 0, because y is a constant. So, we got it as 2. fxx is equal to 2. Next, fyy, that is equal to dou square z by dou y square, that is equal to dou y of dou z by dou y, that is equal to dou z by dou y is minus 2xy plus 20y raised to 4. So, differentiating this partially with respect to y, we get, what is the derivative of first term? Here, minus 2x is a constant. So, what is the derivative of y? That is 1. So, negative 2x plus derivative of 20 y raised to 4. Derivative of y raised to 4 is 4 into y cube. So, 4 into 20, that is 80 y cube. So, this is dou square y by dou x square, that is fyy. Next, we find fxy and fyx. We know fxy is equal to dou square z by dou y dou x. That is equal to dou y of dou z by dou x. That is equal to dou y of dou z by dou x is 2x minus y square. So, differentiating partially with respect to y, the first term contains no term of y. So, its partial derivative is 0, and second term, that is negative y square, its derivative is negative 2y. So, this is fxy. fxy is equal to negative 2y. Similarly, fyx is equal to dou square z by dou x dou y, that is equal to dou x of dou z by dou y, that is equal to dou x of dou z by dou y is negative 2xy plus 20y raised to 4. So, differentiating partially with respect to x, here we are considering y as a constant. So, derivative of the first term, that is minus 2y, because derivative of x equal to 1 here, and whatever derivative of second term contains no terms of x. So, derivative of the second term is 0. So, here fxy is equal to negative 2xy and fyx is equal to negative 2x. So, both are same because the second order partial derivatives are continuous. Our next example is to sketch level curves associated with the given functions. First one, f of xy is equal to x plus 2y, and second one, f of xy is equal to y square minus x. We know what is a level curve. It is given by the equation f of xy is equal to c. So, for the first problem, here f of xy is equal to x plus 2y. So, the level curve corresponding to the first function is x plus 2y is equal to c. Where c varies, we can put any values for any suitable values for c. So, what does this equation represent? This is a linear equation in x and y. So, this equation represents a straight line. So, for any value of c, we get a straight line. So, here I have drawn two level curves corresponding to two values of c. First, I have considered the value c is equal to 1 and then c is equal to 2. So, if c is equal to 1, the equation becomes x plus 2y is equal to 1, and this equation represents this straight line. in order to draw this straight line, we have to consider some points. Here, when x equal to 0, we get 2y is equal to 1, that is y is equal to half. And similarly, when y equal to 0, we get x equal to 1. And when x equal to negative 1, we get y is equal to 1. So, we get 3 points here. So, you mark 3 points in the xy plane. Then, after joining, we get a straight line. So, this is x plus 2y is equal to 1. Oh, this is one level curve. And similarly, for the value c is equal to 2, the equation becomes x plus 2y is equal to 2. Here also, to draw the graph, we need points. So, if you put x equal to 0 here, we get y is equal to 1. If you put y is equal to 0 here, we get x equal to 2. And if you put x equal to 1 here, we get 2y is equal to 1, that is y is equal to half. So, we have 3 points. So, you mark these 3 points on the plane, xy plane. Then we get this straight line. So, level curves. So, these are 2 level curves corresponding to, the first one corresponds to c is equal to 1 and second one corresponds to c is equal to 2. So, level curves are always like this. They will not intersect. We now consider the second example, that is the function here is f of xy is equal to y square minus x. So, the corresponding level curve is given by f of xy is equal to c, that is y square minus x is equal to c, or we can write y square is equal to x plus c. So, our level curves are in the form y square is equal to x plus c, where we can choose any values of c appropriately. Now, what does this equation represent? This is the equation of a parabola. So, here I have taken 2 values for that is c is equal to 1 and c is equal to 2. For c is equal to 1, this equation becomes y square is equal to x plus 1. And what about this parabola? This parabola is open to the right, and what is the vertex of the parabola? It is minus 1, 0, because here x plus 1, that is x minus of minus 1, and here y minus 0. So, the vertex is minus 1, 0, and here also the vertex is minus 2, 0, and I have drawn these 2 level curves, that is these 2 parabolas here, and this one is the parabola y square is equal to x plus 1, and this is the parabola y square equal to x plus 2. Here also, in order to draw the parabola, we have to find points. So, we know one point of the parabola, that is vertex. So, the first parabola passes through the point minus 1, 0. Here, this is the point minus 1, 0, and we have to find further points to draw the parabola. So, when we consider this equation, y square is equal to x plus 1, if we put x equal to 0, if x equal to 0, we get y square is equal to 1. That means y is equal to plus or minus 1. So, correspondingly, we get 0 plus 1 and 0 minus 1. So, here 0, 1 and 0 minus 1. So, these 2 points, we get these 2 points. And again, we put x equal to some 3. If x equal to 3, then y square equal to 4. So, y equal to plus or minus 2. So, corresponding to x equal to 3, we get 2 and minus 2. So, we have 3 points. 3, 2. 3, 2 is a point. 3 minus 2 is another point. So, we got 5 points on this curve, and we join these 5 points. Okay, then we get this parabola. And similarly, in order to draw the second level curve, that is y square is equal to x plus 2, we know its vertex is minus 2, 0. And to find points, we put x equal to 0 here. So, we get y square is equal to 2, that is y is equal to plus or minus root 2. We know the approximate value of root 2 as 1.414, something like that. So, corresponding to x equal to 0, we have 2 points, plus root 2 and minus root 2, and we mark these 2 points here. So, this is approximately root 2 and this is approximately minus root 2. So, we have 2 points, and this point is 0 root 2 and this point is 0 negative root 2. And again, if we put x equal to 2 here, we get y square is equal to 4, that is y is equal to plus or minus 2. So, again we get 2 points, that is corresponding to x equal to 2, we have y equal to plus or minus 2, that is we have 2 points, 2 plus 2, 2 plus 2 this point, and 2 minus 2 this point. So, we have got 5 points to draw this parabola. Now, we join these 5 points, then we get a parabola in this shape. So these are two level curves corresponding to the value c is equal to 1 and c is equal to 2. Now, so what we discussed in this section is that we discussed about functions of two or more variables, and we find partial derivatives, that is first order partial derivatives and second order partial derivatives and mixed partial derivatives, and also higher order partial derivatives. And we studied what is meant by level curve and level surface, and we have drawn the graph of some level curves. Now you have some assignment questions. First one is sketch the level curve associated with the function f of xy is equal to root of x square minus y square minus 1. Sketch the level curve associated with the function f of xy is equal to root of x square minus y square minus 1. So as you know, level curve is a curve of the form f of xy is equal to c. So you equate this to c. So we get root of x square minus y square minus 1 is equal to c. And then square this equation, then we get an equation. That equation represents some geometric figure that you are very familiar. So and you find the equation of level curve and you draw the graph. Okay. Now second one, describe the level surface f of xyz is equal to x square by 9 plus z square by 4. You are also familiar with this term. So this this equation is in terms of x and z. So it is a figure. It is a 2D figure in the xz plane. And you find the shape. You can name that figure because you have already studied this type of equations in your plus 2 classes. Now, third one, find the first and second order partial derivatives of two functions. Two functions are given, z and z. Here z is a function of x and y, and here f of xy is equal to x e raised to x square y. So you find first and second order derivatives, partial derivatives of these two functions. So I conclude. Thank you.